There's 1,000 simulated data values between 0 and 2, according to a uniform distribution. You might wonder, what if I took all the numbers in this data set and squared them and made a histogram, say, of the result? Is that a quick way to do that in Mathematica? Can I do that? Data is a list with 1,000 numbers in it. If I do data squared, it will square all 1,000 numbers. And there's what we get. Interesting. So the original numbers are uniform on the interval from 0 to 2. I square them. It seems like it's no longer uniform on the interval from 0 to 2. Can this be modeled with a probability distribution? Yes. How? Let's see if we can figure it out right now. Oh, this is so much fun. Let's see if we can figure it out. So say X is uniform on the interval from 0 to 2. And when you write this, the tilde is essentially shorthand for has this distribution. X has a uniform distribution on the interval from 0 to 2, continuous. Let y equal x squared. What is the distribution of y? Lots of question marks. By the simulation, it seems like it's not going to be uniform. It seems like the PDF is probably going to have this kind of shape. Well, what is that? Is it exponential decay? It's hard to know for sure. Can it be figured out? Yes, using something called the CDF method. This method I'm going to show you is, I think, super cool. It's not in the book, but I think it's a super cool method. And if you take applied stats from Dr. Wetzel in the spring, I do believe he talks about it from my memory of what he talks about in that class. We'll use it here right now. We'll use it a couple times in the future here. What is the CDF method? The way to figure out, the best way to, maybe not the best way, but one way to figure out the distribution of capital Y is to figure out its CDF first, and then differentiate it to find its PDF. And to see the PDF looks like this, hopefully. What's capital F, CDF of capital Y, not capital X? Let me put a subscript here, capital Y subscript. What is the CDF of capital Y? That's what I'm trying to figure out. Remember, the CDF is always the probability that your random variable, in this case, capital Y, is less than or equal to an arbitrary number, in this case, labeled lowercase y. But how do we do this? Do we have to do an integral? We could probably try doing an integral, but I don't think we need to. Because, well, y is x squared. Maybe I should use that fact. Replace y with x squared. What should I do with this? I'm trying to use the fact that I know what distribution x has. Technically, I know the PDF and CDF for x. That's almost like the CDF for x, isn't it? Because except there's a square there. How do I get rid of the square? Well, how about take the square root? It's a little tricky. Technically, I'd have to write this in general. If I take the square root, it's really the equivalent to saying the probability that the absolute value of x is less than or equal to the square root of y. When you take the square root of the square of something, like I just showed you actually earlier, when I was doing the square root of that, I put the absolute value signs there. technically it's the absolute value signs are necessary. The square root of a number squared is not the number. It's the absolute value of the number. But if the number happens to be positive, then it's the number as well. Or if the number happens to be positive. This being true is equivalent to this being true. Now x is uniform on the interval from 0 to 2. It can't be negative. So this, in this case, happens to equal this probability. Since x is a non-negative random variable, it can't take on any negative values with positive probability. It's uniform on the interval from 0 to 2. It can't possibly be negative. And this is really the CDF for x evaluated at the number square root of y. What's the CDF for x? I know it. That's what I figured out 20 minutes ago. It's that thing with a equals 0 and b equal to 2. Right? X is uniform on the interval from 0 to 2. It's effectively x over 2 when x is between 0 and 2. Yeah, I mean, you could write it piecewise. 0 if square root of y is negative, which it can never be. Well, that's probably best said if y is negative. It's square root of y over 2 if square root of y is between 0 and 2, which is equivalent to y itself being between 0 and 4. Right? If y is between 0 and 4, then square root of y is going to be between 0 and 2. And it's going to be 1 if y is bigger than 4. It's not a linear function in between 0 and 4. It's a square root function. The PDF for capital Y now is the derivative of this. Which will end up being, think about differentiating the middle part here, 1/2 y to the 1/2, differentiate, that'll get 1/4 y to the negative 1/2. If y is between 0 and 4, and it turns out to be 0 otherwise. And what is this? That's the same as 1/4 square root of y, which is a function that has a graph that decreases between 0 and 4. In fact, it's got a vertical asymptote near 0. And when y is 4, it equals 1/8. That's what the PDF is. That's what it looks like. You never would have guessed that unless you did all these calculations. This is a very powerful technique. I mean, yes, I was guessing the graph looked like that, but I didn't know it had a vertical asymptote. You might wonder what the vertical asymptote means. It means as your sample sizes get larger and larger, you can have arbitrarily high numbers of data values near 0. Your sample size needs to keep getting larger and larger. On any interval near 0, any fixed interval near 0, the number of data values can keep getting larger and larger. Is effectively, in a nutshell, what it means. Is this really a PDF? You might wonder that. Is it really a PDF? Did I really find the right answer here? Well, we could confirm that it satisfies the properties of a PDF, like we could confirm that it integrates to 1. But wait a minute, this is an improper integral, isn't it? No infinities in there, but the lower limit of integration, the 0, is a place where you've got a vertical asymptote. So you actually have to calculate it as an improper integral if you do it by hand as a limit. Turns out the limit does exist, and this does equal 1. Yay. It is a valid PDF. That doesn't prove it really models our situation, but it is a valid PDF. You could find out other things about it. You could try to find the mean. 0 to 4, y times this is what you'd have to integrate. Oops. Yeah, I mean, you could simplify that before integrating. You're effectively integrating a square root function. Turns out the mean is 4/3, 1.3 repeating. Does that make sense? It may not make complete intuitive sense. I mean, the original variable is uniform between 0 and 2. Its mean is 1. The mean of its square is not 1 squared, which is also 1. It's 4/3. So maybe that's something a little unexpected, a little non-intuitive. But I believe I have not made any mistakes, so I believe that's right. You could figure out the second moment. Doing that integral is 16/5. You could figure out the variance, 16/5 minus 4/3 squared would be the variance. The square root of that would be the standard deviation. Okay, you could approximate the standard deviation. You could do all your standard kinds of things. More importantly, you could use the PDF and CDF to find probabilities. Okay, you could integrate the PDF, this function, over various intervals to find probabilities, or you could just do differences of the CDF values. Where's the CDF? Right there. Capital. Well, it's ultimately the equality of this with this is what you would focus on for CDF values. You know, capital F of 3 minus 2, capital F of 3 minus capital F of 2 would give you the probability of y being between 3 and 2 and 3. You might also wonder what would happen if instead of squaring x, you do something else like cubing it or raising it to the 4th power. Theoretically, the CDF method should still work, but it probably gets more complicated. You could even ask what happens if you take the sine of x or the cosine or the logarithm of x. Oh my, the possibilities are infinite. Whether they have applications is another question. You might also ask more simply, what happens if you added x to itself? X plus x, 2x? But wait a minute, should you really think of it that way? When you imagine adding x to itself, x plus x to get 2x, should you really think of it as multiplying x by 2? Because maybe you'd prefer doing a simulation 2 separate times and adding the 2 separate results together that will not equal each other. Like the first time you do the simulation, you get 0.4, and the other time you get 1.3, and maybe you add those 2 separate numbers together. So that's not equivalent to multiplying by 2. It might be better in that case to think of the situation in a different way, to say x1 and x2 both have a uniform distribution on the interval from 0 to 2. And we create a new random variable by adding those. And I'm wondering, what is the distribution of that new random variable? That's a harder thing to do, theoretically. We actually need ideas from chapter 5 instead. And it really also depends on some other assumptions. We also might want to assume, maybe because it's simpler, like we did in chapter 2, assume these are independent. They have the same distribution. They have the same PDF, the same CDF. But their values they take on when you do the experiment could be different and vary independently of each other. If you know one, you don't necessarily know the other. Yeah, that's a harder thing. But we are going to do it in chapter 5. But maybe we can try with simulation here today. Maybe what I should do to simulate what I'm talking about here is go back up here. Let's do the random variate again. Let's say data 1 is applying this random variate once, and data 2 is applying it another time. And then I get a new set of data obtained by adding those numbers, data 1 plus data 2. That's going to add the corresponding numbers in each list here. What kind of distribution does this have? Is it normal? Looks like it might be. Bell-shaped curve? Well, wait a minute. It really can't be normal. If you're adding two random numbers that are restricted to being between 0 and 2, the answer can't be any number on the number line. It's got to be between 0 and 4. So it can't be a normal distribution. It turns out to be something called a triangular distribution.